Please join me in welcoming to the Distinctive Voices podium, Dr. Daniela Della Castina.
Thank you, Jennifer. Hey, everyone. Thank you for attending this lecture on a Tuesday evening. As introduced, I'm Daniela, or Danny, and I'm really happy to talk to you today about the OSIRIS-REx mission, which was recently in the news when we returned a sample of an asteroid called Bennu earlier, well, I guess it's not earlier this year anymore, but in September of 23. And so what I'll be doing tonight is spending some time discussing why we developed this mission to visit asteroid Bennu, and then what is ahead of us. Our spacecraft is on a new journey to a new asteroid in an extended mission, which I'm leading. And so I'll end by discussing our new adventure. All right, but just to get started, I want to talk about asteroids in general, why we study them, what they are, and why NASA has invested so much money into developing these robotic planetary exploration missions specifically to explore asteroids. And so this is sort of an overview of all the objects we have seen to date with spacecraft, and they are all shown in scale. This includes for small bodies of a couple different varieties. Several of these are asteroids, including Lutetia, which is the biggest asteroid we've visited by spacecraft, depending on how exactly you define an asteroid, as well as some of the more potato-looking objects that I'm sure folks have seen pictures or artistic interpretations of asteroids, these sort of elongated shapes. The sizes here are all intended to be relatively proportional. And so when we get down here, we start seeing comets, icy small bodies that tend to have similar unusual shapes to asteroids, but are composed of very different materials, ices and volatiles. And then we haven't visited very many. In fact, we've only really visited one, depending on, again, how you categorize things, especially some of the moons in the outer solar system. But we have been to one primitive Kuiper Belt object, which looks a heck of a lot like a comet, called Arrokoth, and that was by the New Horizons mission after its flyby of Pluto. And so these objects, they have heavily cratered surfaces, as you can see, and that tends to indicate that there's not a lot of active processes available to resurface them. So their surfaces indicate that most are pretty old. We do see asteroids predominantly in the inner solar system and comets and things that are composed of ices and volatiles further out into the outer solar system, and then, of course, Kuiper Belt objects at the very edge of the solar system in the Kuiper Belt. But by and large, these small bodies, which range from a couple hundred of, in fact, a couple meters to a few tens of kilometers across, they really represent what was left over after planet formation. And so they provide a lot of good clues. They're really the debris after the formation of solar system that we can use to disentangle our evolution around the sun. And so getting a little more towards that and focusing now just on asteroids, this is a nice diagram of the solar system. It is not to scale, but here is our sun, here are the terrestrial planets, and here are the outer giant planets. And most asteroids reside between Mars and Jupiter in an area called the asteroid belt, which happens to coincide with a line in terms of distance from the sun that we call the snow line. And this is where the snow line existed during solar system formation. So it's represents where during the basically the formation of our planets within the protoplanetary disk. Water ice would condense. It was cold enough for water ice to condense and form grains. And so what currently exists in our present day asteroid belt is a really fascinating combination of objects, some which contain high temperature forming rocky materials and are dominated by things like calcium aluminum inclusions and chondrules. These are things that formed at very high temperatures and then migrated outwards, as well as some objects that seem to have formed much further out in the solar system and were scattered inwards. And as a result, our asteroid belt contains a collection of bodies which really formed in different areas of our protoplanetary disk and now have coexisted through, in large part, migration of the giant planets scattering material inward and resonances with the orbits of Jupiter and Saturn, preventing this material from really coalescing into another object. So this is a fantastic fossil bed, so to speak, of processes that took place across the protoplanetary disk during the formation of the solar system. And every once in a while, we get lucky or unlucky, depending on how you want to think about it, because of those resonances I mentioned that happen as a result of interactions with both Jupiter and Saturn. Sometimes this material gets kicked inward to the inner solar system, and we have a special collection of near-Earth asteroids that sample a lot of different types of these bodies. And so this is fantastic as somebody who works on spacecraft because it means these objects are very accessible for us. We don't need a lot of fuel or long mission timelines in order to reach them. So beyond just studying asteroids from the perspective of somebody who wants to understand the history of the solar system, we also know that these objects have been responsible for pretty cataclysmic events on our own planet. And one of the mottos of the OSIRIS-REx mission has been exploring our past. So this is a nod to solar system evolution and determining, how did our planets form, what were the basic processes that took place, but also securing our future. So this is an artist's rendition of the impactor that was responsible for the Chicxulub impact. It's what is putatively responsible for the extinction of the dinosaurs. And there are a handful of extinction events across our fossil record that can be traced back or can be linked to asteroid impacts. And so we are keenly interested in understanding these objects from the perspective of planetary defense as well. With that, I'm happy to introduce the OSIRIS-REx, which was NASA's first asteroid sample return mission, intended to cover a variety of scientific objectives, but that really bracket, again, this exploring our past and securing our future motto. And so OSIRIS-REx is a heck of an acronym. It stands for Origin, Spectral Interpretation, Resource Identification, Security-Regolith Explorer. And this spacecraft, which you can see a cartoon of here, was loaded up with several different instruments that were intended to cover each of the different components of that acronym. We launched in 2016, and we arrived at an asteroid called Bennu in December of 2018. And I'll just kind of briefly step through some of these instruments because I'll be showing data from a few of them later on. But this is a fantastic spacecraft, probably the most bells and whistles we've ever sent to an asteroid. In that we had several cameras, 3 of which, SAMCAM, which I'll be showing lots of data of, was intended to document our sampling of asteroid Bennu. MapCam is a color imager. Polycam is a very high resolution imager that could go from a telescope to a microscope. We also had two spectral instruments, one that looked at thermal emission in pretty long wavelengths from 5 to 100 microns, and one that went from the visible to infrared wavelengths, 0.4 to 4.3 microns. And so these two payloads really helped us discover the composition of this asteroid Bennu. Then we had a laser altimeter that was contributed by the Canadian Space Agency, and this helped us map the entire shape of the asteroid. And we had some navigation cameras, which were intended, as the name would imply, for navigation, but we ended up using them for quite a bit of science and made some really cool discoveries with them. What you don't see here, but you will see shortly, is what our sampling mechanism look like. And so that's on this component of the spacecraft that's out of the view on this cartoon, but you'll see some videos in a little bit of its arm outstretched. It had about a 3-meter arm with a circular sample collection device attached to the end of it. And the reason that this mission was developed with all these bells and whistles to go collect a sample of an asteroid has a lot to do with the asteroid that we selected, asteroid Bennu. And so I'll go ahead and just jump right on to some of the first images we gathered of asteroid Bennu. But this object is pretty special in that it is something that when we viewed it from telescopes on Earth before the mission had even been developed into a concept, it was incredibly dark. So it has a reflectance of about 4%, which is similar to that of coal. And it is, we had hypothesized at that time that an object this dark only gets that dark because there's a lot of carbon present. And so when we examine carbon-bearing meteorites on Earth that we at the time thought were a good analogy to Bennu, we know that they also have a lot of a lot of water bound up in their mineral structure. So this object seemed very interesting from an origins perspective, since it appeared like it was maybe full of carbon, and also the best analogs for what these objects look like in our meteorite collection also have a lot of hydrated phases present. Sounds like something that might help us establish how did life on Earth maybe initiate, or how did some of the key ingredients for life as we know it become present on the early Earth. And so for that reason, Bennu was selected as the target of the OSIRIS-REx mission, not just to study with that incredible payload that I showed you a moment ago, but also to examine a piece of it returned to Earth in a way that where we had kept it very pristine and had protected some of maybe the more friable or fragile materials present on the asteroid. We do, like I mentioned, have some analogous meteorites available in our collections across the world, but meteorites are probably representative of a pretty biased set of materials because they represent the material that's strong enough to make its way through our atmosphere and survive that whole journey from our upper atmosphere to the surface of the Earth. And so they likely are not representative of the full range of materials that might be present on asteroids. And we've had the opportunity to learn some pretty cool things that confirm that in the short time that we've had the sample back. But getting back to Bennu, we were not expecting the surface of this asteroid to look as rocky as it does. We had planned an entire sample acquisition strategy based on the assumption that there would be very fine sandy material present on the asteroid. And that is in part because when we examined it from the Spitzer Space Telescope, well before the mission ever arrived, it had a very low thermal inertia. And so thermal inertia is this quantity that gives you a sense of how well a material will retain heat. If you think of something like sand on the beach, in the morning, the sand is very cool, and within a couple hours, by the time you hit noon, the sand might be so hot it's hard to walk on. And it's because of its small grain size that it is able to change its temperature very quickly. It does not retain heat very quickly. Think about this in contrast to a large boulder, which might take a long time to warm up in the morning sun, and then that heat kind of slowly radiates out as the sun goes down. I'm thinking a lot of some of the big blocks I saw driving out here, some of those big boulders that show spherical weathering. So anyways, there's this quantity of thermal inertia on Bennu was very low, and we took that to imply that the material on its surface was fine-grained, and that turned out not to be the case. As a result, we had a very hard time choosing a place on this asteroid from which to gather a sample. We had not anticipated that there would be building-sized boulders, many of which you can see as this rotates, that could take our spacecraft out. And our sampling mechanism was designed to ingest pretty fine particles. And so we really had to kind of redesign our entire concept of operations when we got to the asteroid to account for this rocky surface. But luckily we did that, and a sample of the asteroid was gathered on October 20th of 2020. And I will show you what that looked like in a moment. But here is the sampling site that we settled on. So the surface, again, is quite rocky. Here's a 10-meter scale bar just to get a sense for things. The height of some of these boulders is about what you would see from a 3-story building. And so this is one of the smoothest regions that we could identify. It's still pretty rocky. And luckily, we developed some autonomous techniques to help our spacecraft touch down here. And if it had gotten too close to any of this terrain, would have known to abort independent of humans in the loop. And so this site was chosen because of 2 reasons. It was relatively smooth, and we really needed that, and there was a dearth of smooth areas on the asteroid. It was also in the northern latitudes. So I'll see if maybe it rotates into the field of view here in a way that which I can catch right here. And that meant it didn't experience quite as much direct sunlight, solar insolation. So it didn't get as warm, and we saw with our spectral instruments that there was the presence of organic molecules here. So we thought it was probably, from a scientific value perspective, one of the most worthwhile spots. Temperatures were cool. There was the presence, which hopefully enabled longer-lived organic molecules on the surface. They weren't as rapidly broken down by heat. And it had the right kind of terrain. And this is what we had envisioned our sampling technique would look like before we actually did it. So what you can see in this video is touching down with that circular sampling head I mentioned earlier. We would puff some nitrogen gas into the surface that would agitate the material that would then get trapped in a one-way door of our sampling mechanism. And then we would be able to safely back away and stow the sample within a sample return capsule. And I'll run through that one more time. So that's how we expected everything would go. touching down nice and slowly. Just a little puff of material as we interacted with the surface, and then slowly backing away. But as this was sort of the theme across our mission, we were surprised during sampling. And so what actually happened is we penetrated about 50 centimeters into the surface of the asteroid. So that was, it's about from my finger to my elbow. And we probably would have kept going if our back-away thrusters hadn't been triggered to send the spacecraft away from the asteroid. So the surface of this object, for being very rough and rocky, was incredibly weak. The material seemed to have no cohesion, and the strength of the surface was practically zero. So we almost dove into it as though it was a pit of balls that you would see at like a McDonald's playground. This was a surprise, but also was great for collecting samples, since we were totally submerged under the surface when our puff of gas was released. And so it turned out to be a fortunate surprise, but one that, again, really surprised us. And we have learned a lot about the geotechnical properties of the asteroid as a result of this surface interaction experiment that we didn't necessarily intend to have when we planned on a sample return mission. Let's see if there's anything else I want to add. So here's just another view of that. This is from one of our navigation cameras, so it's like a side view. You can right here see the shadow of the arm. And again, we're just spraying a tremendous amount of material. It's a little hard to see maybe with the lighting, but there's just a huge cloud of dust and debris as we back away. So we really made a mess on the surface. And that was very exciting for us to characterize after the fact, because we created a crater. Let's see if this will work. So this is intended to show sort of a pre and post of what the area looked like before and after. And it looks like it's frozen, but basically we were able to excavate quite a bit of material. And that has been an incredible scientific treasure trove in and of itself, because the weak surface of this object has a lot of implications for how we might someday defend our planet against an object like Bennu that could potentially impact us. If we can beat it and send a kinetic impactor to it, similar to the experiment done by the DART mission about 2 years ago, this very weak surface indicates that we should be able to give it a pretty good nudge and maybe knock it off its collision course with our planet. All right, so here is what we, oh no, the color's gone a little wacky. But here is what we reconstructed from that event. So we displaced a tremendous amount of material across the surface, and our thrusters ended up being responsible for a large share of that, which we had never anticipated, and NASA probably would have not agreed to our proposed mission profile if we had known this would happen. Because you can see our spacecraft just got bombarded with material. And fortunately, all's well that ends well. We successfully backed away. We escaped that cloud of material. It did confuse some of our instruments, like our star trackers, but it meant we collected a pretty generous amount of sample. But here is, we took our sampling arm with our sample camera and we examined what happened right after we backed away to a safe location far from the asteroid. And we noticed at that particular point in time that it seemed like we were losing material. And so further imaging of the sampling head revealed that we had collected so much material, we were like a chipmunk with its mouth completely stuffed. And there was one large rock in the center that was jamming the throat of our sampling mechanism. And as a result, it was causing us to leak material. And so we rushed to stow the sample. We had planned to do a maneuver where we had our arm outstretched and we spun the spacecraft around. We did a little pirouette to determine the difference in the moment of inertia of our sampling arm before and after sampling, and that would allow us to get a handle on the mass. We scrapped all of that and stowed the sample as quickly as we could. And so I'll try on my end to adjust the color and see if that works. Yeah, okay, cool. And then we went ahead and we put the sampling head in our return capsule and tucked it in for the long journey home. And then in September of this past year, we clipped that thing off the spacecraft and sent it back home to Earth. And so this is, we've really stretched the heck out of this video in order to make our sampling head visible. This crescent here is the Earth. And we did this after about a 2-year journey to get the sample back home after after the last peak of Bennu that we took post-sampling. And so this was a pretty exciting time. We returned the sample to the Utah Test and Training Range, which is a DoD facility. I was not there when we released the sample or when we collected the sample container at UTTR. I was with the spacecraft team who initiated the sequence of events that needed to take place in order to cut the cord and send this baby home. But it was just an incredibly exciting event because we had worked for so long to build the spacecraft, develop the sampling mechanism. We got to Bennu. It wasn't what we had expected. We had to sort of redesign the mission on the fly, and then to finally get to the point where we could release it and get ready to collect it was just, yeah, it was amazing. This is some telescopic footage of the sample return capsule making its way back down to Earth, provided by the Kyuso Observatory at the University of Tokyo. And so this took place basically in the middle of the night on, in between September 23rd and 24th of last year. And we had a very, very well-coordinated machine to collect this sample with helicopter support provided by the DoD at their Utah Test and Training Range. And this was sort of the nail-biting moment as we watched from DoD assets our sample return capsule. You can see it, it's just right here, make its way back down to Earth. And what you don't know is that we were supposed to see a parachute deploy about 3 seconds into this video. And as you can see, the parachute is not deployed. This object looks like it's tumbling. Things were extremely nail-biting, but and our drogue parachute, which was the first stage of our parachute system, did not go off. However, we had a multi-stage parachute system, and there we go. Our main chute, this orange and white striped object, did deploy, and it had enough engineering margin in the design to fully arrest the fall without the drogue. And so after that nail biter was over, the sample return capsule made a perfect landing. It was actually near a road. You couldn't have asked for anything to be more ideal. We sent an environmental sampling team and some range safety officers to go collect it. So this was a fantastic day, but we just had a little bit of drama at the very end. This is the principal investigator, my colleague Dante Loretta, on the scene to collect soil samples from around the capsule to ensure that we had good documentation of any material that might come in contact with our sample of Bennu. And then we put the capsule in a sling load and sent it away to a temporary clean room that was set up at the Utah Test and Training Range. And the next morning, it was taken by C-130 to NASA's Johnson Space Center, where it currently resides in a curation facility. And so this whole drama was very exciting. But what's even more exciting is now we have this incredible sample in our clean rooms. And so we went ahead and disassembled the sample canister. This is a picture I took of Dante after we took off the back shell of the canister. He's just stoked. In the clean room where the sample lives. And this was one of the first pictures we took after opening things up. So this should look familiar. This is our sampling head. So you saw a couple different views of that from spacecraft imagery as well as some animations. And one thing to note is that the inside of our canister is very dirty. There's this black material all around. And this is, in all likelihood, the result of the sampling canister tumbling through the atmosphere and really getting shaken up. However, it provided an early opportunity to examine the sample because we didn't have to disassemble this entire canister to begin accessing it. And so we have been busy doing that, as well as doing our best to preserve the sample for future generations since that time. About 60 grams was our requirement of the sample, was our requirement of the amount of sample that we intended to gather from asteroid Bennu. It looks like to date we have collected roughly twice that, which is really exciting. And that may not seem like a lot of material. 60 grams is about a quarter of a cup of packed brown sugar. But when we have the opportunity on Earth to study this material at the atomic level, it's a lot. And it's been really, we've already been really thrilled by what we've learned so far. Here's just another view of how much material got across the interior of our canister. And you get a sense for a lot of fines, a lot of really fine powder-like material, as well as some little pebbles. And so it seems like the tumbling and maybe also a gas purge that we had injected into the sampling head to prevent atmospheric contamination early on after the sample made its way to Earth, kind of did a natural size sorting experiment for us. All right, so here are some of the early results. This is what the sample is made of. First off, we see a lot of phyllosilicates. And so these are water-bearing clay materials, and that's the kind of wispy structure that you see in this image, this electron microscope image, which is, the scale bar is 2.5 microns, just to give you a sense of the detail that we're looking at. So this is great. This is exactly what we were expecting based on our remote sensing data at Bennu and our predictions before the start of the mission, that this would be loaded with water-bearing minerals. We also see things like sulfides and iron oxides, including these like magnetite, what we call framboids, as well as some plaquettes that are indicative of aqueous alteration. And so when rocky material gets soaked in water and decomposes, these are some of the byproducts that we would expect to see. This all indicates that Bennu and likely the body that it originated from, because it's probably a reaccumulated impact shard from a much larger body that formed very early on in the solar system, that a lot of water was present in its interior, which is exciting. This is some of the CT scans that we can do of whole particles. So this is a particle about 1 millimeter in its, this is a scale bar just to give you a sense, in its diagonal dimension. And these CT scans are great because we can get really detailed size information for determining densities, et cetera. And we can also look for phases. In this case, red here is highlighting sulfides within the material. So we're doing some pretty impressive analysis on these objects at the pebble and grain level. And probably one of the most exciting things is that the sample of Bennu appears to just be chock full of carbon. And so what you can see here is an optical image of a small grain, and then that same field of regard, but now under fluorescent light. And these bright blue areas indicate what is likely inorganic or organic insoluble material or carbon globules. And this is exactly what we wanted to find at Bennu. In fact, the sample of Bennu, this is based on our preliminary analysis, just of that material that I showed you was outside of the main canister, but our preliminary analysis of that sample shows that this is the most carbon-rich extraterrestrial sample that we have available to us. It appears to be 5% by weight carbon, which is really exciting. When we flipped over the TAGSAM head, you can get a sense for some of the material that we subsequently collected, and this material as well as the material in the interior. So all of this has been collected. The material in the interior we're still working on collecting, but we've already been able to get a jump start on the analysis just from what we've seen what basically fell out of the canister, which is just super exciting. But this material is really dark. It looks in line with what you would expect for something that is really carbon rich. And it's so fun looking at some of these pictures from my perspective, because I feel like I've seen, objects like this, which is maybe 2 millimeters across, or 2 centimeters across. So it's just very similar objects on the surface of Bennu from some of our remote sensing images. So it's great to have everything come full circle. Here's just some more beauty shots. So to date, this is what we have collected and extracted from the OSIRIS-REx sampling head. We are, like I mentioned, still working on getting at some of the material in the deep interior of the canister, and but this is a tremendous amount. We can do years, decades of science with just this, and that's what we have begun. But the mission, well, the sample analysis component of the mission is just getting started. We are also beginning a new journey with the spacecraft. So very shortly after it diverted to avoid hitting the Earth, it went onto a new path, a trajectory around the sun that is eventually going to allow it to rendezvous with this asteroid named Apophis. At Apophis, we plan to do some things really similar to what we did at Bennu, like, fire up our thrusters and get close to the surface and see what happens. But Apophis is a very different object than Bennu. And I'll just spend a few minutes talking about our extended mission to close things out. And there's surely more to come because we're just getting going on this, this new endeavor. So Apophis is an asteroid that is pretty infamous within the community of people like me who study these things, because when it was discovered in 2004, there was a scare that it might impact the Earth with about a 3% probability on April 13th of 2029. And so that might not seem like a lot. I guess how many of you are intimidated by a 3% probability chance of an object impacting the Earth? Okay. No, all right. So, just for some perspective, in any given year, the University of Padova's public health department, public health school, predicts that we have about a 3% chance of a global pandemic. So I feel like that statistic always kind of brings things home a little bit. But fortunately, because this number was relatively high in terms of comparisons with other objects, and it's a very maybe low likelihood, but very high consequence event to have an object like Apophis impact the Earth. It would cause regional devastation. It would be more, it would deliver more kinetic energy than the most powerful atomic bombs that have been tested on Earth. People really paid attention and examined a lot of data on this asteroid that had been taken kind of incidentally, and were able to bring down this 3% to something that felt completely negligible within a few months. But there remained a scare that it would impact the Earth in a subsequent event exactly 7 years later. So this would be in 2036. Again, because this asteroid has been so scary, we have studied the heck out of it and now know that it should not impact the Earth in 2029, but it does get very, very close. And that's what you can see on these two diagrams. So right here is the Earth in blue, and here is Apophis during the 2029 encounter. And here is another view where you can see the Earth centered and Apophis getting within 1/10 of the distance between the Earth and the Moon, which is shown here in yellow. So it makes a very, very close approach. It is the largest object that will ever get this close to the Earth in recorded human history. And it will be visible in the night sky in parts of Europe and Africa. So we will be sending our spacecraft to Apophis right after this incredible near-Earth encounter. And because I'm running short on time, I won't spend a lot of time discussing some of the details of the mission, but I will highlight why we are going there, which is, as I just mentioned, Apophis is one of the largest objects to ever get this close to Earth, and we do think some strange things will happen when that takes place. So what you can see right here is close approach distances of a bunch of different objects, all shown with dots that are relative in scale in terms of the size of their circles. And here is the line for geosynchronous, the orbit of geosynchronous satellites. So Apophis gets below that, and it gets within this range of values where we think the whole asteroid might get resurfaced because of Earth's tidal tug. And so we're really excited to examine an asteroid after something so unprecedented taking place. And stay tuned over the next couple years, because I'm sure you will be hearing about Apophis's close approach in the news, as well as what we plan to do with our new mission, which has been dubbed OSIRIS-APEX for Apophis Explorer, in studying this asteroid. All right, thank you.